Alrighty, I think I'm gonna go ahead and get started. Thank you all for coming today. This is our fourth workshop in our first session in our workshop series. And today we're going to be talking about difference and differential equations with applications to disease modeling. So I'm really excited to present with you all today because we're going to do some really cool math. And this differential equations in particular is a huge part of modeling on all levels. So I really hope that you get something useful out of today that you can hopefully apply to future competitions. That being said, the future competitions, the registration closes in about 2.5 weeks. So start thinking about your team or your advisors if you're wanting to compete in that. I also want to say thank you for being here today and thank you for being present at the last 3 workshops. The participation has been really great. Sorry, don't mind the cat. And yeah, I'm hoping we can keep that up with great participation today and in the next few weeks. Just a reminder that we're being recorded and going up to YouTube after this. So today I'm leading the first hour. I'll be talking to you, like I said, about differential equations. My name is Julie. I go to University of Utah, like all of our other workshop leaders. And then you'll hear from Keshav again to lead us through the second hour, going over some solutions to the problem that we were looking at last week. We have our usual array of volunteers. Thank you, volunteers, for being here. If you have questions, a good place to put them is in the Q&A. That will go directly to our volunteers and they'll be able to answer that without interrupting the lecture. But of course, you can also put answers or questions in the chat. Particularly, that will be useful if I ask you a question looking for participation. So those are our 2 features there. And I think with that, I'm ready to get started. Did I miss any announcements, Keshav and Wesley? Great. Then let's get going. So what is a difference or a differential equation? What makes them so powerful is that they are pretty broad and can apply to almost anything. It is basically just saying something that changes. Usually it's over time, but it doesn't even have to be. It could be over space, for instance, but we're going to stick to time today. So when we have a change over time, that's usually called a rate, right? So solving these, we can go from a rate to an amount, and that's what makes these so powerful. So they're used in all sorts of modeling. We're going to talk a little bit about disease modeling today in a couple different contexts. They're also really common in ecology. That's where I have used them a lot in the past. A classic example is predator-prey cycles. Physics uses differential equations, genetics, all sorts of medicines, really anything that you can think of. My research considers modeling sea ice. So you can use differential equations to describe sea ice change. You could ask any of the volunteers and they'll probably tell you a different example of when they've used differential equations in their own research. So what is it? Let's get to some math. A difference equation is what we're going to go over first because it's a little bit more simple, hopefully more familiar, and it is involved with a discrete system. So that means something that marches through time point by time point, rather than a continuous timeline like we'll see later. So in this case, the value at the next time is going to depend on the value at the previous time. So in this first equation, that's where we will write n I plus 1 equals a n I. So n is our amount here. It could be anything. It could be amount of infected people in a population. That's what we're going to talk about later. So we can then kind of break this up. So what would n, or what would this coefficient a actually be? Well, the amount of people at the next time, it's going to be the people who were there before, plus the number of people who were born, maybe. Okay, so now we're switching to people. And then minus maybe the people that died in that time. So this B delta T, this is a birth rate times the amount of time between time points. And similarly, D delta T is a death rate. And then the rest of the slide, we just go through some algebraic manipulations and end up writing it so that we have a fixed or a very explicit form for the coefficient A. So we converted A into this a little bit longer, but more descriptive way of writing that coefficient. We can go a step further and rearrange this so that it looks like this. And now here is where we're remembering what we said on the first time is the change over time. So this is going to be the change in the number of people over the change in time. This is very evocative for how we are going to write differential equations. So that's why we put it here. But if you're just going to use a difference equation, there's nothing wrong with using, one of the first two here. Great. So I'm going to go ahead and do a few examples throughout this lecture. And the first one is one that we actually saw last week. So you'll remember that we were looking at an SI model last week, where we had S as the number of susceptible and I as the number of infected at a time t. And the way that we had written this was the susceptible at time t equals the susceptible at the time before plus a constant times this interaction. And we can tell that this is a difference equation because we have t and t minus 1. So we're looking at the change from a previous time step until the next one. And similarly for I. Yeah, so difference equations, maybe all those equations on the last slides, made you a little nervous, made you a little scared, but you've already seen one, you've already worked with it, and hopefully we can just build more intuition and more examples for when they might be useful. Next. Okay, great. So I'm going to go into another specific example, and these are stage structured models. So a stage structured model is a discrete time system where you have two or more distinct types that convert between one or the other, and for that reason we can describe it by a matrix. I will hopefully make this more clear when we go through an example. The most common application is with population ecology. So we can see why this is really useful because we have these different stages. For instance, lots of animals, you have eggs, juveniles, adults, and they all grow and develop according to totally different rules, right? You wouldn't say that the eggs, juveniles, adults all die at the same rate, for instance. It can be really different, especially, for something like fish that have lots of eggs, but not all of them make it to adulthood. Similarly, the adults reproduce where the eggs and juveniles don't. So this is a huge application of stage structured models. Another one that I thought of is enrollment at a university. So for some reason, your question asked something about, how does enrollment change in light of these things? You could create a stage structured model where you have your different levels and have different exit probabilities, stuff like this. We're going to talk about an example of disease spread because that is our theme for today. So let me go ahead and get on to that. So what we're talking about right now is going to be a non-communicable disease. This is different from what we talked about last time because we're assuming that the disease is not contagious. So it doesn't matter. So for instance, last time, I'm going to start writing and hopefully we can see. Great. We had that S of t equals S of t minus 1 plus A S t minus 1 I t minus 1. And now this right here is an interaction term. So this says that if there are no infected individuals, then we can't gain new, oh, I think this was probably a minus, wasn't it? Well, anyway, the disease can't spread without infected individuals. In a non-communicable disease, something that you could get, for example, through just random chance, something like cancer or something from the water, right? You don't need that interaction term. And that is very key for why we can actually write it as a matrix. So I'm going to go through this example, and I'm hoping that you will help me write a set of equations to describe this system. So we're considering two types of animals. We're going to have healthy animals and infected animals. So we assume that the healthy animals get the disease at a rate of 20% a year, and they have different survival probabilities. Healthy animals survive at 15% a year, whereas infected animals survive at 5%. And they all reproduce at a constant rate of 1 offspring per year. I'm going to go ahead and write the first term corresponding to A, so that hopefully you get the idea and can give me the other terms that correspond to 2 and 3. So by saying that healthy animals get the disease at a rate of 20% a year, that's saying that the number of healthy is going to be, so based on this, only 0.8 times the number at the previous time step, because the other 20% go into the infected category. Okay, I'm hoping this made sense. And I put pluses here because we have more terms to deal with from 2A and 2B. And I'd like to give you just maybe a moment in the chat to either ask questions if this isn't making any sense, or give me the terms that come from the survival. I'll give you just a few minutes for that. Okay, so I'm not getting a whole lot of answers in the chat, and maybe that's because things are confusing, or we're tired, or anything like that. I will go ahead and fill in the rest of these equations, but if, again, anything is not clear, please do ask. Oh, okay, and I do see a question in the chat now. Reproduction, is that before or after the animals die? I'm going to say for simplicity before, but this is a really good question, and it is going to lead into part of our motivation for differential equations, because you're right, this stuff doesn't happen at discrete time points, right? They're reproducing and dying kind of all at the same time. So that's a really good question, and thank you for asking that. So when we're talking about survival, the afflicted animals, those are infected, right, have a survival of 5% per year. So the only ones that survive on to the next time point are, oh no. Let me get my pen back, excuse me. So that will be plus 0.05 infected at T-1. Similarly, that the healthy survive at 15% a year, that's going to be 0.15 healthy T-1. Finally, the reproduction. Like we said, we assume reproduction happens before death or anything, kind of arbitrarily, and they all reproduce at a constant rate of 1 offspring per year. And we're assuming, I guess I should have written, it's a healthy offspring. So on our healthy equation, I'm kind of running out of room, but we're going to get a plus h of T-1 plus I of T-1. Okay, so this final term is for reproduction. We assume that all the infected, all the healthy, they create 1 healthy offspring. Okay, hopefully this is starting to make a little bit more sense. And we are going to go ahead and switch over. Well, actually, I think I might have one more slide before we go over and actually look at this in MATLAB. Okay. Just want to make sure these don't show up on the next slide. Great. Okay, so how do we analyze these models? We built that equation that I just erased, but we will see again. And what we're going to do is we're going to write it as a matrix. So matrices are super well studied in math, and we have analyses of them using eigenvectors and eigenvalues to determine long-term behavior. And we will see that in just a second. So right now I'm going to go ahead and switch over to MATLAB. This is the example that we were looking at. Hopefully you will agree that it is the same numbers that we were using. We have our constant survival rate. Oh, I think I had this wrong actually in my previous slide. Okay, so this has to do with the transition from healthy to ill. It's actually going to be a minus 0.2 of the healthy because they're moving from the healthy to the ill. So sorry about that. Hopefully that wasn't what was confusing you, because that was, I think, the first thing I wrote. Oh gosh. Okay, well, hopefully that is cleared up now. I'm really, really sorry for that. And then we have our survival and our reproduction. So we can write this as a matrix. Hopefully you will agree. If I were to collect all of the healthy terms, the coefficients would add to 0.95. So that's why we have that in the first category. Okay, I'm actually gonna write this out maybe before going back to MATLAB. I'm sorry, I'm kind of back and forth right now. So we have healthy at t plus 1 is the 15% survival minus the 20% that move into the infected category, plus the reproduction, which is 1 healthy plus ill. And then similarly, we had I, t plus 1, we had a 5% survival. And then we're getting that 0.2 from the healthy. So I'm hoping to convince you that I can write this as a matrix. And how I'm going to do that is by making vectors of the population at t plus 1 and multiplying it by that same vector at time t. So now what I do is I can collect coefficients to put in the matrix. I'm not sure how many of you are familiar with matrix multiplication yet. I think that might be a bit more advanced topic. But the way that it works is when you multiply matrices to get this entry, you multiply this first slot with this one, and then you add the second slot multiplied by the ill. So in this case, we know that the contribution from the ill at time t is just going to be 1, right? That's the only thing that comes from the infected population. So this right here is going to be a 1. On the other hand, the healthy, we can collect all these terms, and we are going to end up with, let's see, a 1 minus a 0.2 is 0.8, and then we have to plus a 0.15, and we get 0.95 here. Okay, I'm going to fill in this one here. So we know that the contribution from the infected at time t to the infected at time t plus 1 is 0.05. And hopefully now, if things are starting to make sense, you guys can tell me in the chat what the last number should be to fill in my matrix. So once again, that question was, what should go in this last spot to understand the contribution to the infected at time t plus 1 from the healthy at time t? And we have used most of the constants. So hopefully, maybe just by pattern recognition, if nothing else. Okay, great. It is 0.2. So now that we know where this matrix came from, I'm going to switch over to MATLAB. And you can see that we just created this exact same matrix here. Now what we're going to do is we're going to start with an initial population of 1,000 healthy animals, and none of them are infected. What we're going to do is find, so let's see. I wish I could clear that, but I don't. Okay, so then we're going to plot this generation after generation, or year after year, I should say. So the first thing that we're plotting is just a vector from the origin to the first point. So let's thinking about it. Okay, and it kind of gave it away, it did it all at once. Maybe, well, anyway. So our initial vector is just this blue one here. How we move forward a point, one time point, is by multiplying by this transition matrix, right? And we get our population at year 1. So we can then plot that vector on the same plot using these plotting functions that we learned last week. And we see that year 1, we move up to this red line. So we now have about 200 infected, which makes sense. That's 20% of the population, and a little bit less than that of the healthy. If we do this twice more, we just keep multiplying by the transition matrix time after time. And we see what has already been plotted by MATLAB is we're kind of converging to this single direction, and that is called an eigenvector. That direction would be. And then what is important is that we see that once we're on this direction, we stay on that direction. So if I were to include a 4th year, I would multiply the transition matrix by my population at time 3. And then I can overlay it with the same command, except now I'm using top 4. And now let's see if I can we're just going through the whole thing. Sorry, I'm a little bit new using MATLAB Live, so give me just a moment. Okay, so now population 4 is this green one. And you can see that compared to population 3, which ended right here, we're growing. And that was what has to do with eigenvalues and eigenvectors. So if we look at what our eigenvalues were, we could get it with the MATLAB function eig, and it is 1.13. So that means that each time that you multiply by a vector in that eigendirection, you're going to increase your population by a factor of 1.13. So this is important for conservation, because if this eigenvalue is smaller than 1, it means you're going to decrease your population each time, right? Until eventually you have no more animals healthy or infected. With an eigenvalue positive, then we're going to keep growing the population. So this is important to keep in mind. So how these eigenvalues change with different parameters. Let's say that if instead of 1 offspring a year, they only reproduce half an offspring per year, then our eigenvalues are still positive, but it's not growing as fast, you see, or still greater than 1, I should say. And we can see how the effects of other parameter changes might influence our growth. Okay, so I'm going to head back to my slides now, and we're going to start talking about differential equations. Let's do it. Okay, so you will remember this equation from one of the first slides, and how we change this from a discrete time system where things only happen, once a year in that last example. Things happen all the time. So instead we change our delta t to a number so small that it's practically zero. It's basically continuous now. And that's what we mean by a differential equation. And we denote it with d's now. So instead of I plus 1 and I and a delta t, we're using dn dt. And it's the same thing now where we have the birth minus the death. Right. This equation is going to describe the rate that the population changes over time, where the d on the right-hand side, it's like the difference between I and I plus 1, if that difference was so small that you couldn't even see it. Right? What do we do when we have a differential equation? There are a lot of different methods to deal with it. We can solve it by hand in some very nice cases, but this is very difficult and not always possible. What we can do is we can use other methods to make it tractable. We can use a differencing scheme. So that's basically doing the backwards direction where we start with the differential equation and then make t big enough to see and write it as a difference equation. Now that is something that we can code up in MATLAB and see how things iterate over time. However, there are some given functions in MATLAB that will do the solving for you, basically turning it into a difference equation for you with some fancy tricks to deal with certain problems that come up when you're trying to solve them. And they're pretty easy as long as you know how to use them. But once again, stick with whatever you're comfortable with, especially in the competitions. So our differential equation has the following solution. We can figure that out by hand. And we see that now our n of time t is an exponential equation. So that means that this equation corresponds to exponential growth or decay, depending on the sign of b minus t, right? So I have just a little bit more in MATLAB to show you with respect to that. So this first here is thinking about an iterative difference equation. So we're now looking at that n equals b minus dn again. And if b minus d is the coefficient 1.1, then what we can do is find the next n by just multiplying the last one by n. So let me go ahead and run through this block. Okay, so it showed up right here how our n is changing throughout time. We started with 1, right? That was our initial n. And then we multiplied by 1.1 and 1.1 and 1.1. And we got this time series of 10 time points. We could plot that. Not sure why it plotted everything all at the same time, but that's okay. And we see that we know the exact equation as well, right? It's that exponential that I showed you on the last slide, and we can compare them. So we use our plotting that we know how to do now, and we look at the difference, and they're actually quite similar. So this seems like a pretty good thing. We could put in different numbers. So if A was not 1.1, but 0.9, we would see decay instead of this exponential growth. Okay, flipping back and forth a little bit more. Let's look now at disease modeling. So we're going to go back to SI and SIR models. So once again, thinking about communicable diseases rather than the non-communicable example. And now what we're going to do is include this new phase of recovered population. So you can start as a susceptible individual. You may get the disease, but you may recover from it and no longer be able to get it. These are the differential equations that describe this model. So this is very similar, you will see, to what we looked at last time, but we just went from the discrete time to the continuous time, right? And once again, we see this interaction term because if there are no infected, then we can't grow the infection. Everyone is just going to stay where they are. And stay where you are, of course, corresponds to zero change, which means ds dt is zero, di dt is zero, dr dt is zero, right? And we assume that people recover at a rate b, so that's why people are moving out of the I category into the R category at rate b I. We can modify it, make it more interesting if, perhaps immunity wanes, right? We're seeing this right now in the real world with COVID. You recover from COVID, but after a while you may become susceptible and you can get the disease again. So that's what we mean by this last arrow. One more MATLAB example. So what we are going to look at here now is, I went too far, the SIR model. So what's important in MATLAB is that when you have functions to give to a certain method, in this case we're using ODE 45, the functions are defined at the end of your file. So let's scroll down to our SIR function. This is exactly what we saw on the last slide. So we see that ds dt is just negative a times s times I. So we look at our little key here. S is going to be y of 1, I is y of 2, and R is y of 3. So y is a 3 vector that contains the number of individuals in each state. And then once again, we are recovering at rate b, and then going into the recovered category. So this is how you have to define a function in MATLAB. And then how we're going to do this function, our function is called SIR. What we're going to do with it is we are going to put it into ODE 45. So I mentioned that as one of our equation solvers. The other arguments that we give it are just t, and those are going to be the time points that we want to evaluate the equations. So I'm going to say run this over 20 years, say, and at every 0.1, give me back a value, and that's what I'm going to plot. I also have to give it an initial vector. Why not? So we're assuming that we start with 100 susceptible and 1 person infected. No one is recovered. So now, once I put all that information into ODE 45, it gives me back the y's at each of those time points that I asked for. And then what I'm going to do, of course, is I'm going to plot them. That's our favorite thing to do, right? That's how we look at our equations and analyze them. So we look at our S values, and that is the first column of y, and we can view this on this plot over here. Great. And then we might compare this to some data that we have or something, or if this was a competition, we could think about what parameters need to change so that it looks more like the data, that kind of thing. We can also think about plotting just each of them on their own, right? Because this plot actually looks pretty different from this one. So if we look at just the susceptible, we can really get a better look at what's going on by this smaller scale. Right? We see that we started with 100, and then we get down to something like 87 or so susceptibles, and that's pretty much where we stay. Similarly, we see that, okay, by year, maybe this is 5, the infection is pretty much down to 0, and everybody is just constantly there. Another thing that we could look at is the plot R versus S. Okay, I think that I didn't mean to do that. I'm sorry. This last subplot should just be R versus T. So let me rerun that. Okay, and now we can look at R versus T. So we end up with something like 14 people recovered. We can look at R versus S to see maybe how those things are related, the number of people recovered versus people susceptible. Great. And that was my last MATLAB example, but I just wanted to come back here and talk a little bit more about what other things we can do. So this was our first simple modification, is that assume that people can lose immunity from the disease. We can also add in another stage, and that would be an exposure stage. We can think about what happens if there's a vaccine. What if it isn't fully effective? And think about how that would change. One of the parameters of changing between the 3 or more states, or how it might be its own state, and we can add more states. So I think that this is a really powerful example. Okay, so we already looked at these plots, and we saw that the leveling off is corresponding to steady state. That's 0 change, right? Okay, so like I was saying, this is a really powerful framework for modeling not only diseases, but a lot of communicable things or infectious things. So maybe you'll remember the first week we talked about vaping in high schools. And actually quite a few of the teams with that were competing that year used SIR models or versions of them to answer this question or to model this question. So these are exactly the same equations. Hopefully you'll believe me. They just changed the names, the letters corresponding to their states. And you can see a plot very similar to what we saw already. We have the decrease and then the steady state. And what I think is actually super interesting is that the winning submission used a modified SIR model. And this is their figure to denote how this was working. So pretty much it's very similar. This main stuff is just simple SIR, but they also assume this extra category of not susceptible. Maybe some people just will not vape no matter what. And I think that's a perfectly valid assumption to make. It doesn't matter how many of their friends are doing, some people will not do it. They also included a death pool, right? So that's another thing to think about. And this doesn't have to be, mortality death, but, maybe it could also be exiting high school, basically just getting out of the system that we are concerned with. And then these are the equations that they used to model this thing. And of course, there's more to the winning submission than they chose the best model. Like they also had a great write-up and all of this kind of stuff. But it's interesting, I think, that you can use this framework in such a way and make really cool, powerful results. Okay, I think that is all I have for you for this first hour.
Okay, welcome back everybody. For our second hour, we're going to be doing another submission analysis. Today, we're going to be tackling the 2017 M3 challenge problem. Last week, Wesley took us through this question, or at least the first part of it, and we thought about assumptions to make, maybe some information we'd like to know through research, some independent variables and model parameters. And then we started to think a little bit about how we could piece this all together into some kind of model. Today, we're going to be looking at solutions from teams that have submitted and kind of critique them a little bit. The very first thing I want to do, though, is I want to go and remind you all about the scoring guide. The scoring guide can be found here, and I will put this in the chat and also take us there. So this is a PDF document that is available to everybody, and pretty soon it will be right here in the chat. This is kind of the first sheet that's given to judges so that they know what to look for in your solutions. And so this is obviously a really good idea for you all to look at so that you know what judges are looking at. I'm not going to go through this entire document, but I highly, highly, highly recommend that everybody takes a look at this. I'm going to just read off a couple of excerpts from this back here in my slideshow. So towards the beginning of this document, it says, for each of questions 1 through 3, teams should create a mathematical model, which means define all variables and parameters with units, justify assumptions, describe the mathematical approaches used in the model, apply to or demonstrate for any situations presented, discuss implications of the results, right? And hopefully in these first couple workshop sessions, we've really tried to drive home the point that defining your variables and parameters with units is important, justifying your assumptions is important. We've just gotten started in our lecture series with Julie's lecture on describing mathematical approaches used in the model. So if you wanted to use a difference or differential equation, you would be able to kind of explain your reasoning there. Apply to or demonstrate any of the situations presented, which is basically fancy talk for make sure you answer the full question that's given in the problem statement, and discuss implications of the results. Give a little bit of a discussion, make sure you answer the question like very clearly, do a little bit of a sensitivity analysis, maybe talk about the strengths and weaknesses of your model. These are all things that judges are looking for and will make your presentation or your report really stand out. Okay. Another thing later on in the scoring document for other concerns or other things that judges are looking for, check that the units are consistent. All figures and graphs should have a title, label, caption, axes should be labeled. All tables should have a title, header, caption, label. All variables and parameters should be clearly defined. Motivate and fully explain the use of any complicated mathematical expressions. And when citing outside sources, clearly explain what statistics, models, equations, or insights you took from each source, right? Again, these are things that you should be thinking about when you're writing your own report. How are judges going to be viewing the work that you've done, the figures that you've made, the graphs that you've made, the words that you're putting to page? And today what we're going to do is we're going to be looking at other people's solutions and with this in mind, so that we can kind of think about what should go into our own presentations, our own reports. So as I kind of mentioned, our game plan for today is we're going to be looking at 3 different solutions that teams have given to the 2017 first part of the problem. And in particular, we're going to spend a lot of time thinking about the assumptions that each team made, the model that they made and the variables that they used in the model, and how they presented their results. All right, so some questions that I think are going to really help us when we're analyzing these are, do they follow the scoring sheet guidance? Did they kind of hit these check boxes that are in this document? Are their assumptions justifiable? Now, I'm not asking, are their assumptions good? I'm asking, did they back up whatever assumptions they made with evidence, with maybe some statistics, with some kind of citation to back up any claims that they make? Is their work easy to understand? Can you read through in maybe a limited amount of time and understand the kind of pathway that they took to get to the answer that they got? And are their results easily interpretable? Again, if you're just kind of quickly looking through their reports, are you able to understand what their results mean? And did they clearly answer the question that you had asked them, right? Okay, so this is the game plan for today. What I'm gonna do first is just remind everybody what the problem statement that we're gonna be looking at is. and I'll read this out. This was, again, part 1 of the 2017 question. Tides of change. Build a mathematical model to determine a sea level change risk rating of high, medium, or low for each of the 5 parks below for the next 10, 20, and 50 years. And these are the 5 parks. You may use provided data on sea levels to build the model. Explain your interpretation of high, medium, and low. Could your model realistically predict those levels for the next 100 years, right? So there are a lot of different pieces of this question. We have to create a risk assessment of high, medium, and low, and we have to explain that interpretation. And then for the next, certainly at least for the next 10, 20, and 50 years, we have to assign one of these risks for each of these times for each of these parks, right? Okay, so as a little bit more of a recap for what we did last week, Wesley took us through, there we go. Wesley took us through some initial assumptions and some questions that we might have. And these are kinds of things that Wesley had thought about and what we had kind of discussed last week. So MSL, or the mean sea level, isn't significantly affected by severe weather events. This is kind of an averaging argument. If a hurricane comes through one of these parks and raises the sea level just temporarily, and then the hurricane kind of dissipates, we don't really need to worry about the sea level change in that tiny little stretch of time. The next thing, the missing sea level data, mean sea level data, can be linearly interpolated. Wesley also showed us in the data set that was provided to us. In some places, there's just not enough data in certain spots, or there's kind of a blank spot where some data should be, and we have to figure out what we're going to do there. Lastly, the change in mean sea level is driven by melting glaciers and ice sheets or expansion of water due to heating. There's actually a lot of debate in the climate science community as to which one of these matters more. So some teams will talk about one or the other. Some teams will try and put both in. But this is, again, up to your kind of interpretation of the problem and what you think you'll be able to tackle in the time given. All right. So with that, what I'm going to do is I'm going to flash a whole bunch of text at you in the next slide. This is going to be the assumptions from one of our team's solutions. And I will ask you a couple of guiding questions that hopefully you will be able to answer in the chat. So I've just taken a screenshot of one of the reports and put all of the assumptions that they gave for part 1 here in this text sheet. Some questions I have for you all: are these assumptions well justified? And a similar question, which of these, if any, has the weakest justification? So I will give you about 2 minutes to read this over and give your thoughts in the chat. I'll give you about another 45 seconds. Yeah, great. All right, I got a couple. Yep, I got a couple of good responses in the chat. So I think I agree. I'd like to hear a little bit more about this second assumption, right? Not to say that it's a bad assumption, but one that I would like to see maybe a source, maybe some data, maybe they did some statistical analysis with the data they had, and they showed that, you know, there's not a whole lot of correlation between certain things that allows them to make this claim. But certainly this is not necessarily a bad assumption, right? Just one that might not be as strong as it could be. Option, you know, or assumption number 1 and number 3 are certainly good, simplifying assumptions. So number 1, I would say we just have to kind of trim down the kinds of things we're looking at in order to be able to answer this question, right? Again, I would like to see maybe a source or something that kind of says, well, we don't really need to worry about tectonic shift. Perhaps over the course of 100 years, we do need to think about this. Perhaps we don't. I don't know. I'm not an expert on that. The third one, we got one comment about how it's a little bit confusing. And I think I don't disagree. I think I would like to just see a little bit more writing to kind of, when you're justifying an assumption. The idea is that, you know, if you take the maximum elevation of this park and the sea level has gone past that tallest point, then that means that the entire park must be submerged, theoretically speaking. And so I think that's kind of their justification, and this kind of leads to what this team will think about in terms of what risk means. Okay. Great. Yeah. Thank you everybody for your responses. The last thing I would just want to quickly ask, does anything else stand out about this? Maybe how this is written or how it's presented in this report. If you were reading this report, is there anything that you would like to change about the way that these are written, about any of the structure, anything like that? We'll give you just a little bit of time to maybe ponder that. I'm not going to spend too much time on this last part, but I'll kind of periodically ask questions like this. One thing that I want to kind of point out is that the formatting of this is just a little bit awkward, right? This is a little annoying to me, the fact that this is not as justified as everything else. Although, you know, if you told me to write a report in 14 hours, you can't expect that much better from me, right? So I'm not gonna bash on them too hard here. One thing that I do like is that they wrote clearly justification underneath all of these headings, right? So I know, okay, this is the assumption, this is the justification. If I'm a judge reading through this, I want to be able to kind of say, boom, 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 this is exactly what they're saying, right? So I do really like this. Right, yeah, just other things that they can add. We do need to worry a little bit about the amount of space, right? We only have a 15-page report, and I will kind of show an example of this later on, where a team kind of gives a lot of information, but they also spend a lot of space talking about their assumptions or kind of justifying things. So there's a balancing act here, and we'll talk about that more. Okay. Great. What I'm going to do is we're going to move on to a different team's assumptions, and I'm going to ask the exact same questions. So this is yet another thing. I'm going to give you again about 2 minutes, and I'll ask you the exact same questions. Are these assumptions well justified, and which of these, if any, has the weakest justification? Give you all another minute or so. If you're still in the process of reading or writing, I'm going to keep going, but please give me any of your thoughts as I'm talking. I also want to thank Wesley for a clarification. I misspoke when I said that the reports are only 15 pages long. They are actually 20 pages long, not including any code that you choose to include as part of your report. But any figures, anything like that, do count for the 20 pages. Okay. So I would say that this document is nicely organized. It's again kind of in a similar vein of, here's the assumption right here, and then the justification is kind of in its own little bracket, so that judges again can kind of clearly read here. Most of these, or at least half of these assumptions, have citations kind of incorporated in here. One thing that I really like, this kind of gets back to what we were talking about in our previous example. This team actually chose to write down part of their justification in terms of the statistical analysis they did. So clearly they tried to fit some data to a linear, a polynomial, and a logarithmic line, and nothing really worked. Their R-squared values were very, very low, which means that you don't have a good regression type model, right? And then they used this as justification. So they told us that this was the case. They didn't show us, kind of explicitly. If you were allowed to have an appendix, I would have loved to see this in an appendix, but in this report, this is more than enough to show that this team clearly thought about this and they did some analysis. They just didn't have the space for it in the report. So this is a great way of conserving some space, but while clearly justifying their assumptions here. If I had to choose which assumption was probably the weakest, again, I kind of like a lot of these assumptions, but I would maybe reword assumption number 3 here. They say all sites start at a baseline of having no predisposed greater risk than another. I'm not sure if I agree with that statement outright, but I think what they're trying to say is we're going to look at a relative change in risk at each park. So if you just assume that the risk level of a park is 0 right now because none of them are flooded, let's say, and then we kind of advance our model and see what happens over time. But I wouldn't say that any park has, one park might begin with a higher risk than another. So I might just reword this one a little bit differently. But certainly not a bad justification or not a bad assumption. Okay. Any other kind of ideas or anything else that stood out to you about this list of assumptions? Or maybe if you had some comparisons between this set of assumptions and the previous one that I just showed you, give you maybe, I don't know, 30 seconds or so to type your thoughts in the chat. Okay, again, I'm going to keep going. Let's see. Yes, so this comment that I just got, I think is makes sense. There's a lot more written in the justification section, right? Even though it might take longer or take more amount of space, right? You kind of buy into these assumptions that they've made a little bit more, which helps you buy into the results of their model, as we'll see later on today. So I think that, you know, your justifications, while might not be the most glamorous part of your report, is certainly something that you should take very seriously when you're writing. And again, in terms of kind of organization, I think that this organization is quite nice. Again, you can read off the assumptions really quickly. They're kind of short blurbs that usually only take one line, maybe two lines, and then the justification is a lot more detailed. If you did want to read their justifications, you're able to. Okay, great. Let me know. I got another question in the chat. Can you please explain the justification for the third one? Let me make sure evidently some sites are more likely to be favored, are more likely to be favored more than others from the start for being safer or riskier than others. However, randomness and variables contributing towards risk cannot be totaled. And in general, in creating a general model to apply to any site, we limit it to ubiquitous factors. Layman's terms, from what I gathered from that, is if you wanted to consider every single possible situation where you could have a change in mean sea level rise, you're going to have a really, really big model that is untractable for the amount of time that they were given. So clearly they tried to just normalize things so that everybody started off on equal footing, so that they didn't have to worry about, okay, well, you know, Olympic National Park is already having, you know, some effects of climate change right there. But we're not going to consider that right now. It's just about the sea level rise, and everybody starts out on equal footing. But yeah, I think this is a simplifying assumption that, again, I would like to see a little bit more explanation. But the idea is to kind of simplify the setup of the model so that things work out a little bit more smoothly. Hopefully that makes a little bit more sense. Let me know if I'm not giving people enough time to read these assumptions. I know today we're just going to be doing a lot of reading and interpreting. So if anybody would like a little bit more time, I'm trying to give everybody 2 minutes to think and then also write in the chat. So if you'd like a little bit more, just let me know and I can increase the time. Okay. I'm going to do one more round of these assumptions. So these, a little bit less writing, a little bit less reading. Hopefully this is a little bit easier on you all, but I'm going to again ask the exact same questions. Are these assumptions well justified? And which of these, if any, has the weakest justification? And then for completeness sake, does anything else stand out between this set of assumptions and the previous two that we've already seen? I'll give you all, well, maybe I'll give you all maybe like 2.5 minutes. I'm going to give everybody about another minute. Okay. Again, if you have any extra thoughts or questions, please give them in the chat as I'm talking. I got one comment from one of our volunteers. I am not showing you right now the residual plots, but they did put all of the residual plots, and I will show them to you later in this presentation. So they're referring to those, but they didn't explicitly refer to them in terms of like figure number 5 or anything like that. But they certainly do that a couple times here. So all of these assumptions are justified. Again, the justifications are a little bit short, and then it's more of a kind of report structure kind of thing. They've included the assumptions and justifications kind of all lumped together, which makes it a little bit more difficult to read. If you wanted to know what their assumption is and then why they justified it, it's a little bit nicer if they're separated out. Some things that, and I think one of our participants actually beat me to it. Number 4, a visual check suggests that this thing is true. Basically, is like the textbook version of "it is obvious that," or "one can show that," which is not really a good justification in a report. So I would flesh this out, and I would, if they were going to give a plot, and they certainly gave plots in this example, to kind of flesh this out a little bit more. Why what about the visual check suggests this? Or maybe if there's a more quantitative way of explaining this, if it's that obvious, right? Another thing, right? Assumptions, the number of them. The first one I showed you had 3, I think. The second one had 4. This one had 5. So it's a little bit difficult to say exactly how many assumptions you're going to need. Certainly, if you have less than 3 assumptions, I would kind of raise my eyebrows a little bit. But you also don't want to take up like tons and tons of space on all of your assumptions. So I would say, I actually don't really want to tell you how many assumptions you should have, but you should highlight the most important assumptions, particularly ones that are simplifying assumptions. So like assumption number 1, definitely you need where you say that you're not going to assume anything about moisture, temperature, atmospheric pressure. This is a very good assumption to have in your model or in your write-up. Okay. So I guess I'll kind of mention right now that I've kind of gone through each of these assumptions, but the 3 samples we're going to be looking at for the rest of today are these. I'm just going to scroll. Oops. Hello. Sorry. This sample right here is from the number 1 winning solution from this year. This one is from a kind of mid-tier, like middle of the pack kind of solution, and then this one right here kind of was closer to the bottom. They basically were able to give a solution to the first part of the problem, and then they weren't able to really get much out of the other 2 parts. So this is how I've kind of stratified our samples for today, so that you all can kind of get a sense for what's a really good, what's top tier, and what's maybe not going to get you very far. Okay. We got about half the time left. So now what we're going to do is talk about the models that each of these teams created, the independent variables and the outputs that they all created, and then talk a little bit about how they showed their results. But as a quick refresh, this is a slide straight out of Wes's presentation from last week. Some initial variables and parameters that we thought about were obviously the mean sea level for each part. This was data given to us from the competition. The percent increase or decrease of the mean sea level for each park. Again, this is something that could basically be extrapolated from the data that was given. The amount of land per height above sea level for each park. So this kind of gives you a little bit of information about the amount of land that each park has at different heights or different altitudes. And then seawater temperature near each park. Again, if you were thinking about your mean sea level rise being a direct result of temperature, then this is certainly something that you would want to include. Okay. But now I'm going to jump straight into one of the samples models and their inputs. Oops. Oh, excuse me. No, I'm not. I also wanted to just remind you all what kinds of models we were thinking about generating for something like this. We thought about a statistical model. We thought about a differential equation model, which now we know a little bit about thanks to Julie, and a probabilistic model. And I've highlighted or I've bolded option number 1 and option number 3, because these are the options that the teams that I've shown you have all kind of bucketed their solutions into. Okay, so this is the solution from the winning team. They did a probability kind of argument. So I would like you all to read over this section and answer the following questions. What variables or parameters, if any, have not been defined? And is this model understandable? Can you read through this and kind of get a gist of what is going on here? Again, there's a little bit more of difficult questions. I'm going to give you all a little bit more than 2 minutes again to kind of read this over and hopefully give your thoughts in the chat. And I wrote this here, but I will also explicitly say that I just didn't want to overload you with more and more text, but this parameter mu and sigma is defined earlier in their paper. I'm going to give everybody about another minute. Yeah, once again, if you have any more thoughts or suggestions, please give them in the chat as I'm talking. Let's see. Oh, I did get one message in the chat. It's not that understandable because it lacks visual presentation forms. So one thing I will say about this solution specifically is that they do give an example of how they actually compute all of this stuff later on. So hopefully that might clear things up. They do kind of, there are no visuals, let's say, but they do like explicitly show how they computed for, let's say, Cape Hatteras or something like that. And then they give their final results. But yeah, certainly this is something that you might want to think about. But again, it's a balancing act. How much space do you have versus how much do you want to be really, really good at explaining your model? I would say in general, this is a fairly decent kind of explanation. There's not too much. There's not too many words, but they do get to be kind of bogged down in some stuff around here, right? This is a pretty large paragraph. The table is nice. It's a really good thing to add. But I will say that I think that there's a slight typo or something. I think they meant to have another column break in between here, or maybe some kind of comma or something here. If you'd like me to kind of interpret what I think this is saying, let n be defined as a normal distribution, or you can also call it a Gaussian or a bell curve. And the mean is given by this thing right here, and the standard deviation is given by this thing right here. So now suppose little x is some number that's given by this normal distribution. What is the probability that x is greater than this number? And in this case right here, under the same situations, what's the probability that x is between these two numbers? And then finally, given the same situation, what is the probability that x is less than this number right here? And whichever one of these probabilities is highest that is the risk assessment that they will give to that national park. Each national park will have their own mu and sigma, and the time is obviously the 10 years, the 20 years, or the 50 years. Okay. Great. So I think part of this is because there was that little bit of a typo. It made it a little hard for me to understand. But again, only 14 hours to write this report. What more can you expect, right? But again, this was from the winning solution. They certainly were able to really drive it home with their results. Oh, sorry. We kind of talked a little bit about issues with the model and maybe just a little bit of more understanding, kind of conceptual, or how they wrote the report, I should say. This is how they gave their results. And so just quickly, I'll give you maybe just a minute here. Take a look at this chart. They gave it right kind of at the bottom of their results section. What are some good or bad qualities about this table that's shown here? And does this explicitly answer the question that was given in part one of this problem? Give you all another 30 seconds. I got a great question in the chat, and this is partly because I just didn't give you all of the information. One question is, how do they define the risk levels here? So let me go back to this previous slide. Oops, previous slide. So these numbers that are written inside these probabilities are how they defined their risk levels. So if this is what this is saying in words, is if the mean sea level rise is most likely going to be greater than this number, then you're at a high risk. If the mean sea level rise is going to be between these two numbers, then you're at a medium risk. And if the mean sea level rise is going to be less than this number, or is most probable, I should say, to be this number, then you have a low risk. And they actually show how they computed all of these different numbers. I just didn't get bogged down into the details there. But to our other comment, I think that this is a great example of how you can very clearly, how a judge can just kind of skim through your report and say, wow, I know exactly what their answer is, right? Because I can see all of the parks here, I can see all of the different years that the problem asked for, and very quickly figure out what their risk assessment is for each of these parks. So I thought that this was really nice when you're reading through here. This really gives you, I think, gives the team kind of nice brownie points. And also there's a clear title, there's some clear headings in all of these columns here. So it's really easy to follow along. Okay. Great, let me just make sure that I've got all of, yes, great, okay. So now I'm gonna move on to another sample problem. This is the model from a different team. So now again, I'm gonna ask the exact same questions. What variables or parameters, if any, have not been defined? Can you understand this model? And can you identify any issues with this model? So again, I'm going to give you about a minute, or excuse me, a little bit more than 2 minutes to read over this and give your thoughts. give everybody just about another minute or so. Right. Okay, great. I got a couple of responses in the chat. So some good things about this model. I think one of the really great things is that I clearly know what every single variable is, right, and what it does, and its units, right? So very clearly in this kind of chart here, or this kind of list here, I know exactly what each of these variables represent. If it was given in a table, that might be kind of nice. One thing I will say is a little bit of a knock is that they don't tell us what any of these numbers are. They give us some references for where they got these numbers, but there's nowhere in this document where they say, okay, well, the initial elevation for Cape Hatteras is blah, right? So I would have liked to have seen that explicitly given. I would say this model is fairly understandable. It's a linear extrapolation, basically. So I would call this a statistical kind of model. There's a little bit of conversation going on in the chat, so let me just check here. One of our volunteers mentioned, does elevation equal sea level? This is actually a conversation I might have had with Julie like a couple months ago, but apparently the elevation of something is not literally just the height from the shoreline to the tippy top or wherever you're measuring. It has something to do with how much water is displaced when this object is put in water. Anyways, it's something a lot more complicated. That's not just directly related to how tall the water is. So that might be a little bit of a sticking point, but I think what elevation here, what they're referring to is literally what is the difference between the sea level and the highest point in the park. At least that is my interpretation of this problem. Let's see, again, making sure. Yeah, so there's not really much of an explanation of what constitutes high, medium, and low, and we're going to continue to see that as we look at this later parts of this problem. Let's see. Yeah, so one person commented, is there a way for them to set a weight on the local and global changes? Do they matter? I think Julie also mentioned, somebody mentioned, yes, Julie also mentioned that, local and global, in some ways that they're already kind of paired with each other. So you have to make sure that they're separated out. What are the local changes over the global changes? And maybe the local change matters a little bit more than the global change. This is certainly an extension that you could do. Any issues with this model? I kind of have one issue with the model just in terms of its formulation. Based off of what I have interpreted this model to say, imagine, if you will, that delta L, both of these are positive numbers. Okay, so the average yearly change in sea level locally and globally is a positive number. Time is certainly a positive number. This initial elevation is going to be a positive number. So that would imply that this elevation is actually going to be increasing as this change in sea level increases. So maybe this is correct if we're thinking about what Julie's thinking, and this is supposed to be sea level and not elevation. Well, no, it says elevation of the park at future time interval, right? So it's certainly the land. Somehow the land is getting taller as the sea level is rising, right? So again, 14 hours, what are you going to do, right? If they'd put a negative sign right here, I would have said, sure, whatever. I think that makes sense. But this is, Something to think about. Certainly a judge would kind of think about this a little bit, what happens when these values are positive? Does that give me the result that I'm interested in, right? Some simple kind of quick calculations can help you figure out, A, is your own model good, and B, help you identify when there are problems with models. Okay, so now I'm going to show you what the results are for this team. So immediately there's zero break. Immediately they give you these 5 plots, and then this text is all they give you, and then they move on to the next problem. Okay, so I'd like to ask you all, what are some good or bad qualities of these tables and figures, and do they explicitly answer the question? I'll give you all a minute and a half or so. Give everybody another 45 seconds or so. Okay, please continue to give your ideas in the chat. I'm gonna kind of start talking here. So some good things about these figures is that they're very clearly labeled. They know their units, and I know their units, and I know exactly what this plot is telling me, right? They definitely do a good job there. They, again, their units here, so I know exactly what's going on. Even though they have nice plots, I would say maybe this isn't all that necessary, right? Because we're looking at just a linear fit to data. And so we could maybe just condense this all into a table as opposed to showing plots. Oh, excuse me. They definitely take up quite a bit of space showing all of these plots when they're just plotting lines, right? I would say that they definitely do not explicitly answer the question here, right? They kind of tell you from these graphs, a positive slope will indicate that a park is at a low risk, and the negative slope implies a larger risk. So I think what you're supposed to do is kind of walk back and forth between this text and these plots and say, okay, well, this is low, this is low, this is larger, whatever that means. This is low, this is larger. And then they add this extra little comment here that I'm not totally sure what they're implying here, because nothing here has negative values on the y-axis. So I'm not totally sure what they're referring to here. Right, but these are kinds of things that we should be thinking about. They don't explicitly answer the question as nicely as the previous team did, right? A nice table that just says low, medium, high, and something like that is great. Anybody could look at that and tell exactly what they're thinking. Right, another comment is that they didn't even define what a moderate is, right? Because the problem explicitly asks for low, medium, high, and we should explicitly define what low, medium, high is somewhere. The scales on the plot aren't consistent. Personally, I don't really like millimeters here because the elevations are really, really big. They've got to be at least in meters, right? You can tell by the fact that at least all of these are 3 orders of magnitude. Yeah, at least all of these are 3 orders of magnitude. So you could easily convert to meters, but again, that's just a very tiny knock. But definitely hurts like readability a little bit. Any other kind of comments? Let me make sure that I didn't miss anything. Okay, great. So again, make sure that your results at least are very, very readable and very quickly readable throughout. Okay. Now we're going to take a look at our last sample for the day. I think we have about 8 minutes, so I think we might be able to get through it. So once again, here's the model. And so what they've done behind the scenes is they've done a regression analysis, and they have come up with a bunch of coefficients here. I just didn't add that, add all that description. But in terms of text, this is pretty much the amount of text that they gave us. So take a look at this. And as usual, here are the 3 questions. What variables or parameters, if any, have not been defined? Is this model understandable? And can you identify any issues with this model? Again, give everybody about 2 more minutes. Make sure to give everybody another minute. Okay. So I'm gonna say once again that it's really easy to criticize other people's work when you don't know who they are or anything like that. Obviously, we could criticize different people's works until the cows come home, but we'll just we'll try to take a little bit more of an objective view here. There's some small things here like the units are inconsistent between these. Personally, I don't think that this column at all is all that necessary because this information and this information is exactly the same. All you have to do is just convert the units and the information is the same. So not totally necessary here. I would say that this section is a little bit lacking in terms of text. I'd like to be able to read the text to figure out what's going on here a little bit, but clearly whatever information that they're giving us is very nicely organized. I know what all the units are. I know exactly what park I'm looking at in this next one. So what they've done here is they've kind of done a little bit of a statistical analysis on top of a probability analysis. So they use this regression line to come up with these means and standard errors at these different time points. And now they're going to do something similar to what the winning solution did, which is come up with a probability of something. And I'll show you that in a little bit. Right, so, and I'll show a bunch of plots in just a second, which will answer one of these comments that I just got that they didn't really show their data and the variables aren't clearly defined. Okay, so now in the next plot or in the next this next slide, this is all the data that they showed. And so if you might recall from earlier on, one of the assumptions or one of the assumption pages that we were looking at said a bunch of stuff about residual plots. And so here are the residual plots that they were referring to. They gave us all of these residual plots, excuse me, and all of these scatter plots to figure out what the regression information was. And then all the way at the bottom, they gave us this little chart. So P, and they did define this explicitly at some point. P is the probability that the park is not completely submerged at this time. So Acadia, for example, Acadia park has at 10 years out has a 0.997 chance of not being completely submerged, and so on and so forth. And then they define what low, medium, high is based off of these probabilities. Okay. So this, I think it will be the last kind of round of this. I'll give you another minute or so. Let me know what are good things about these plots, what are bad things about these plots. Do the results clearly give an answer to the question asked? Any other comments or anything like that you might have? Give everybody another 30 seconds. Okay. So the two comments I got just now were about how nice this table is. And I think that just speaks basically about everything, right? Colors are really nice and underrated. It is so easy to read this plot. Even if they didn't explicitly tell you what each of these colors represented, I think red, yellow, and green are just so ubiquitous colors for us to understand low, medium, and high risk that it's easy to see exactly what they're saying. So again, table is very, very clear. Let's see. Another thing is that personally, I think that they spent a lot of time showing all of these figures when they might not have needed to. Maybe if you have a little bit more of a statistical background, you really, really care about seeing residual plots. As a judge, I might not care about seeing every single residual plot, maybe one representative one, and just say all the other ones kind of look the same. Might be enough for me. Again, I'm not totally sure if I needed to see any of this, but they also didn't give us any extra information like an R-squared value. I don't know how good these fits are. They look kind of like all over the place, and this line sort of kind of fits this curve. So I don't really know what the R-squared values are here. But other than that, the results are very clearly explicitly stated. And so I know what their final answer is, and that's great. Okay, with that, we are exactly at 6 o'clock. This is great. I did have a little bit of information about part 2, but I was not expecting us to get this far. So I'm just going to skip over all of this and kind of get to our last slide here. So what we did here is we asked ourselves, is it easy to identify the assumptions in the model and understand them and figure out what their justification is? How did we, were we able to understand the model and what variables are? We talked about pros and cons, and we talked about what we liked, what we didn't like, right? We can be kind of fickle when we're looking at other people's work and say, I don't like how this is organized. I love the colors, things like that, right? These are guiding questions that you should think about, and also take a look at the scoring sheets. And if you're interested, Michelle, actually our M3 Challenge representative, gave this link earlier in our chat, and I've also added it here to our Google Slides. This will take you to MathWorks', the M3 Challenge's website, where you can find all the information about this particular challenge. And if you go to Winning Solutions, you can see all the winning solutions here. If you also go to our Drive, this is linked again in the YouTube link, as well as one of our volunteers has just put all of these links available to you. If you go over here to the M3C 2017 samples, you can see the samples that I mentioned, 1, 2, 3. Where's 3? 1, right? 1, 2, 3, as well as some other ones that I've added. Let's see. So I encourage you all to take a look at these reports in a little bit more detail and see if you can understand what they're each of these teams are trying to do and take a look at some of the more advanced problems that we weren't able to get to, and try to think about what you would want to do differently. With that, we are just over time. So again, thank you very much for your participation. I hope you kind of see that if we have a little bit more conversation going on, this certainly makes it easier for everybody to understand what's going on. We will be meeting next week, and Xiao will be taking us through probability type models. With that, I will bid you all farewell.